Good morning, all students. Some again new students are admitted in our division. So for these students, I am sending again the user ID and password. Join first. So we'll start. So in the last lecture, we started the chapter coordination compounds. It is having 7 marks weightage, and we completed the introduction part. What is mean by ligands? What is mean by coordination chemistry? This part is already completed. What is mean by Levy's acid-base interaction? Then different types of ligands. What is mean by ligands? Ligands are nothing but these are the donor groups which donates electron pair to the metal and coordinate bond is formed. So I think on Saturday and Sunday there was a holiday. We revise all this part: monodentate ligand, which is having only one donor group. Then polydentate ligands, again these are classified depending upon the donor groups. If the two donor groups are there, these are called as bidentate ligands. This is a good example, ethylene diamine. Then oxalate, it is also having the two donor groups. Then tridentate ligand, tetradentate ligand, then hexadentate ligand. EDTA, this is the example of hexadentate ligand. Why it is hexadentate? Because there are 6 donor groups, 1, 2, 2 nitrogens and 4 oxygens are there. So this part is already completed. What is mean by ligands and what is mean by different types of ligands. This many times asked for board exam. Remember ambidentate ligand. This ligand actually having the two donor groups, but when the coordinate bond is formed, see, when the coordinate bond is formed out of these two donor groups, one is only used for the donation of lone pair. So there are very two famous examples. One is NO2 and one is SCN. See, once again, I'm explaining because this is many times asked for the board exam, is ambidentate ligand. This ligand is having the two donor groups. See here, this bonding is shown metal and oxygen bond. Means here the oxygen is used its lone pair to form the bond with the metal. And also the nitrogen can be used to donate its lone pair and this bond is formed. So the bond may be from MNO, MONO or MNO2. This same is shown here in this diagram. And another ligand is SCN minus. Again, this in SCN there are two donor atoms. One is sulfur and one is nitrogen. If sulfur is used for bonding, such type of bond is formed. And if the nitrogen is used, this type of bond will be formed. So this ligands and different types of ligands. This is very interesting part. Already I have completed. Then these are the different terminologies we are using in coordination chemistry. Many students are absent in the last lecture, so again I am going to repeat this part. What is meant by this coordination sphere? So see, what is the whatever the included in the square bracket, it is called as coordination sphere. Means coordination sphere contained one is a central metal atom and the ligands are attached. So this is a very discrete structure, we cannot separate it, and such type of compounds are called as a coordination sphere. See, coordination sphere is always included in the bracket, and outside the coordination sphere there are counter ions. See, in this diagram, in this example, K4FeCN6, this included in the square bracket, this is a coordination sphere, and outside the square bracket, these are called as counter ions. These counter ions can be, if dissolved in water, they forms ions. So that's why these are called as counter ions. Then this part is also completed. Charge, what is the charge number on the complex ion and what is the oxidation state of metal. This is calculated by just addition. Also, I have taken this example how to calculate the charge number. Charge number is nothing but whatever the charge on the complex. It may be positively charged, it may be negatively charged. If the positively charge is present on the complex, these are called as a cationic complex. And if this negative charge is present on the complex, it is called as anionic complex. So the how to calculate the coordination number, it is also completed. Just I will take one example and I will start the next part. So if the ligands are bidentate, now you know what is meant by bidentate ligand. The ligand which contains only one donor atoms, these are called as bidentate ligands. And if the bidentate ligands are there, see this example carefully. In this example, we can see, so the what is first we will discuss what is the definition of coordination compound. Coordination number is nothing but coordination number of a central metal ion attached to the monodentate ligands is equal to the number of ligands attached to it. See, in this example of this coordination compound, one example is given. We can clearly see 4 ammonia ligands are there and 2 chloride ligands are there. So the total 4 plus 2 is 6. So the coordination number of this compound or this complex is 6 because 6 monodentate ligands are attached here. Why I'm repeating this? Because this is asked for board exam for 1 mark. What is the coordination number of the given complex? Such type of questions will be asked. Now, in case of bidentate ligand, the condition is quite different because as the name bidentate is there, bidentate means 2 donor groups are there. So we can take this example of ethylene diamine also, and we can take the examples of C2O4 also. So in case of bidentate ligand, the definition of the coordination number is quite different. And in case of monodentate ligand, the definition is different. In case of bidentate ligand, the coordination number depends upon the number of electron pairs. See, I will explain this example. Consider this example here. FeC2O4 thrice 3 minus. See, in this complex, C2O4 is a oxalate ion. C2O4 is a oxalate ion. You know, oxalate ion is a bidentate ligand. And see, how many oxalate ions are there? 3. One oxalate ion gives 2 electron pairs because 2 donor groups are there. Then as there are 3 oxalate ligands, so the electron pairs involved in the bondings are How many electron pairs will be involved? 2 plus 2 plus 2 means 6 electron pairs will be involved. So the coordination number is 6, remember. So this is a quite confusing part. That's why I repeated again. Coordination number when the monodentate ligand is attached, and coordination number when the bidentate ligand is attached. Bidentate ligand or any ligand other than the monodentate. It may be tridentate, it may be tetradentate, it may be hexadentate. What we have to remember, how many electron pairs are involved, we have to check. One bidentate ligand means 2 electron pairs are involved. One tridentate ligand means 3 electron pairs are involved. Remember this. So the definition is different for bidentate and uh, uh, different polydentate ligands. So just it is a revision, and depending upon this coordination number, see, shape of the molecule is responsible. Linear or either tetrahedral. If the coordination number is 2, the shape of the complex will be linear. If the coordination number is 4, there are two shapes, tetrahedral and square planar. And if the coordination number is 6, the shape of the molecule will be octahedral. So in the next slides we will discuss, and this is a double salt and coordination complex. I will not repeat again. This is a very important theory. Remember, those students who are absent last lecture, this Werner theory is, Werner is the name of the scientist who first give the explanation regarding the coordination complex, how the coordination complex are formed, how many types of valencies are there, what is primary valency, what is the role of secondary valency. So those students are absent in the last lecture, they can call me personally or they can message me personally. I will give the important concepts or important things which are important for the board exam. So this Werner theory, don't neglect this Werner theory. Werner studied many coordination compounds and he explained this theory. So according to Werner's theory, at a glance I will explain. According to Werner, there are two valencies. One is primary valency and another is secondary valency. So again, according to Werner, this is a secondary sphere. This is a primary sphere which can be ionizable. Means if this sphere dissolved in water, this forms ions, and this is a very tightly bonded. This do not gives ions. So this Werner theory is important for board exam for 2 marks. Any 4 postulates we have to write. So this all the part is completed. This experimental observations, this problem also I discussed at the time of the lecture. And this is a classification of complexes. Within 1 minute I will explain because this is very simple. Homoleptic and heteroleptic complexes. See, homoleptic complexes means in which the one type of ligands are involved in. We see in this complex only one type of ligands are involved, and in case of heteroleptic complexes there are two types of ligands, more than one type. It may be 2 types, it may be 3 types, or it may be 4 types of ligands are involved. So this is very simple to identify also. When one type of ligands are involved, it is homoleptic complexes, and when the 2 or more than 2 types of ligands are involved, it is called as heteroleptic complexes. So why this part I am repeating again, because this is as for 1 mark, this is also as for 1 mark, and don't lose your marks, because this chapter is a very small chapter and weightage is 7 marks. So all the students should get 7 marks. This is a classification again depending upon the charges. See, cation, as the word cation is there, this complex is having plus charge. See, we have to check the charge on the complex. See this example Zn NH342 plus. Because till the nomenclature system I didn't explain, we can read the complex like this. Zn is a central metal atom, then NH3, 4 NH3. See the coordination number is 4 because this is a monodentate ligand. Now, such type of questions you should answer. What is the charge on the complex? What is the coordination sphere? Which is the central metal atom? Then how many ligands are there? These ligands are monodentate or bidentate. Now you can give the answers of these questions because you know the basic things of coordination compounds. See, as the positive charge is there, this is a cationic sphere complex, and if the negative charge is there, this is called as see, this complex is having negative charge, but this complex is not having charge. But due to this K3, we get here 3 minus C, FeCN6 3 minus, because this will be ionized in water, and it will give 3K plus ions. And if this is 3K plus ions, this complex will get the minus charge. So at that time also I explained, when this K is any counter ion, if it is on the left hand side, the complex is anionic. And in case of cationic complex C, here if the ligand is on the right hand side of the square bracket, this complex will be positive, because this is having the negatively charged, and this is the complex is having positive charge. So if the no any charge is given and the counter ion is given, also you can identify the complex is cationic or anionic. Then the neutral sphere complex. In this neutral sphere complexes, as the name suggests, neutral sphere means there is no any charge is present. See clearly, no any charge is present, and outside the square bracket there is no any counter ion, so there is no possibility of the positive charge or negative charge. Only secondary sphere is given here. The secondary sphere means which is given in the square bracket. Those students who are absent, all the concepts again I have explained. Also I have sent the notes of these lectures. Those students who didn't got the PDF of this chapter, message me personally, I will send it again. Now today we will start this very important part, that is a nomenclature of coordination compounds. Up to this nomenclature compound, all the part is completed, covered. We can read in the notes, or you can read in the textbook also. IUPAC nomenclature system of coordination compound is quite different than the organic compounds. In case of organic chemistry, we learn about the IUPAC nomenclature system of alkanes. We learn about the IUPAC nomenclature system of alkenes, then alkynes, then all the chapters already completed. Aldehydes, you know, it ends with methanol, ethanol, propanol, pentanol, like this. Select the longest chain and identify the groups. But the rules for IUPAC nomenclature system for this coordination compounds are completely different. Completely different means we do not select the longest chain, or we do not identify the functional group. No any functional group is there. So please carefully listen this lecture, because this nomenclature system of coordination compounds is completely different. I will explain the rules first. See, the rules for naming the coordination compounds recommended by the IUPAC are number 1. First one, in naming the complex ion or neutral molecule, see, complex ion, it may be positively charged or it may be negatively charged. That's why the word is given here. Complex ion means whatever the charge on the complex, or neutral molecule. Neutral molecule means there is no any charge. So if this complex ion or neutral molecule is given, name of the ligand will be given first. Means you know the meaning of the ligand now. So name of the ligands, again I am explaining you. Ligands are the groups which are attached to the central metal atom, which is having capacity to donate the electron pair, and the coordinate bond is formed. This is called as ligands. So name of the ligand we have to write first, and then write the name of the metal. So I will explain all the rules first, and then we will discuss the nomenclature system. Today we will discuss all the rules. So what is the rule number 2? The names of anionic ligands. Now see, anionic ligand means what? Anionic means the ligand having negatively charged. Means there is a negative charge on the ligands. If the ligands are negative, the name of the negative ligands are obtained by changing the ending IDE to O and ATE to A2O. I will explain what. When a chloride is there, chloride is, negatively charged ligand. When the chloride is there, in the nomenclature system, you have to write at chloro. If the bromide is there, we will write bromo, like this. Means it ends with O. And if the carbonate is there, for example, carbonate, it ends with ATE. We have to write carbonato, like this. Carbonato, it ends with A2O. When the negative ligands are there, see, anionic ligands means when the negative ligands are there, we have to do such type of change. Then number 3 rule, the name of a complex is one single word. Remember this one. The name of the complex should be one single word, and there must not be any space between the different ligands names as well as between the ligand name and the name of the metal. Means we have to take care when you are writing the word of the when you are writing the name of the coordination compound, you should not give some space between the name of the metal and name of the ligand. So we will understand this because we will take many examples, at least 20 examples I will give you. I will explain you. So don't worry about the nomenclature. First, we will discuss the rules one by one. So what is the rule number 4? After the name of the metal, write its oxidation state in bracket. See, after the name of the metal means after writing the name of the metal, write its oxidation state in Roman numbers, which appears in the parenthesis without any space between the metal name and parenthesis. Means, in simple words, I will explain. When you are writing the name of the metal, its oxidation state we have to write in bracket with Roman numbers without any space. Without any space. So what is the rule number 5? If the complex has more than one ligands of the same type, then the number is di, tri, tetra, penta, hexa, and so on. This is very simple. When the more number of ligands are there. So if the 6 ammonias are there, we can called as hexamine. If the 2 chlorines are there, you can call dichloro. If the 3 cyanides are there, we can call tri. So if the ligands are more than one, you can use this di, tri, tetra. We know these words. In 11th standard also, we heard about this di, tri. Tetra means 4, penta means 5, hexa means 6, then hepta, 7, octa, like this, so on. So what is the rule number 6? For the complex having more than one type of ligands, they are written in an alphabetical order. See, this alphabetical order is very important. For example, here is given. Suppose the 2 ligands with the prefix. Don't consider the prefix. We have to consider the name of the ligand here. So one is a tetra aquo ligand. Aquo means it is water. Tetra aquo, and one is dichloro. See, alphabetically this chloro C comes second and this A comes first. So we have to write the name tetraaco first, and we have to then write the name of dichloro. So don't see the tetra or di. We have to check the name of the ligand. Remember here, many students get confused here. We have to consider the ligand. Don't consider its prefix. Don't consider its prefix alphabetically. So for arranging the ligands alphabetically, consider the name of the ligand. Here aqua, A comes first, and this chloro, C comes later. So don't confuse. This T comes later and D comes first. So don't take this prefixes. Consider the ligands. So this is the rule number 6. Then what is the rule number 7? I am coming to the rule number 7. If the name of the ligand itself contains numerical prefix, for example, ethylene diamine, you know this ethylene diamine. Ethylene diamine, it already contains di word. So if this situation is there, if the ligand itself contains the number and there are 3 ethylene diamines, then what we have to do? So we have to use this prefixes tris for 3 and bis for 2. So the name of the ethylene diamine, if there are 3 ethylene diamines, the name nomenclature will be like this: tris. Tris stands for 3 ethylene diamine, because this di word is already, it is used in the ligand. We are using this tris word, tris. Tris stands for 3 ethylene diamine, and bis stands for 2. This bis will be for diamine. If the 2 number is there, it will be bis ethylene diamine. If the 3 word will be there, it will be tris ethylene diamine, and if the 4 is there, it will be tetrakis. Remember, so it will be that bis, tris, and tetrakis, like this. So the last rule is rule number 8. The metal in the cationic or neutral complex is specified by its usual name. Remember, we are coming to the metal. When the metal in cationic or neutral complex is specified by its usual name. In case of the cationic and neutral, means when the complex is positively charged or when the complex is neutral, we are giving its usual name. For example, if the iron is there, we will write iron like this. If the cobalt is there, we will write cobalt, and if the aluminum is there, we will write aluminum. But when the anionic complex is there, anionic complex means when the complex is negatively charged, it ends with ATE. It ends with ATE, means Fe is there, it will be ferrate. If the aluminum is there, it will be aluminate. If the cobalt is there, it will be cobaltate. If the gold is there, orate will be there. Then Ag is there, it will be argentate, like this. So we will coming to the examples now. See the IUPAC names of some anionic and neutral ligands are shown here. See, in the nomenclature system also we discuss about this anionic ligands and how it, if the negatively charged ligand is there, the IUPAC name will be bromo. It ends with O. See, if the bromide is there, it ends with the name will be bromo. If the chloride is there, the name will be chloro. If the fluoride is there, the name will be fluoro. Iodide is there, the name will be iodo. If the cyanide is there, the name will be cyano. Sulfate is the, see the sulfate, it ends with ATE. It is quite different. So it the name will be sulfato. Then the carbonate, it ends with ATE. So IUPAC name will be carbonato. Remember, carbonato. If the AT is there, it ends with ATO. And this nitro is there, it the name will be nitrato. Nitro, it will be nitrato. Then carbonate, carbonato. Hydroxide, hydroxo. Oxalate, oxalato. Then this is nitrate. Sorry, nitrite, NO2 minus and NO3 minus. Don't confuse these ligands. This is also the negatively charged. This is also the negatively charged ligand. Many times students get confused. This NO2 minus is nitrite, and the name will be the nitro for nitrogen bonded ligand, because this is a ambidentate ligand. Remember, this is ambidentate ligand. There are 2 donor groups. Nitrogen is also donor, oxygen is also donor. So at the time of complex formation, which atom is used, we have to remember. This is also nitrite. In this, oxygen is bonded. See, when the oxygen is bonded, but the name is quite changed here. This will be nitrito, and this is nitro. So see the difference between these two, nitro and nitrito. When oxygen is bonded, it becomes nitrito. Then this is a thiocyanate. Again, this is a ambidentate ligand, NCS and SCN. See, this is a thiocyanate. This is called as thiocyanato. When sulfur is bonded, these two ligands are ambidentate ligands. Remember, There's a nitro and this is a thiocyanate, which atom is used for the bonding is very important. If the sulfur is used, the name will be thiocyanato, and if the nitrogen is used, the name will be isothiocyanato. So these are quite confusing. Make a practice of this nitrate and this thiocyanate. So all these ligands are anionic ligand, means which is a negatively charged ligand. Now I am coming to the neutral ligand. See, this ammonia is neutral, so name will be amine. Note the spelling. Note the spelling is very important here. Ammonia, and the spelling of amine is different. AMMINE. Then CO, it is a carbon monoxide ligand. The name IUPAC name it will be carbonyl. Then this is water. This is completely different. The name of the water ligand in case of IUPAC, this is used as aqua. Remember, this is the IUPAC name. Don't use this water word when you are going to write the IUPAC names. Then EN, we are familiar with this ethylene diamine. Ethylene diamine, the same name is given here, ethylene diamine. So confusing, I will notice the confusing part. It is this one, these two, the nitrite, when oxygen is bonded, when nitrogen is bonded, this is a thiocyanate. So special give concentrate these two ligands, give special what you can say, special concentration, give special concentration on these nitrite, thiocyanate and this aqua. So these are only confusing, otherwise all the names are familiar with you. And this amine, ammonia is considered as amine. So these are the some names of anionic and neutral ligands. Now I am coming to the name of some metals. So one IUPAC rule is there: when anionic complex is there, it the name of the metal ends with ATE. So see the metal here, aluminum metal is there, it will be aluminate. Cobalt is there, it will be cobaltate. Gold is there, it will be aurate, because see the symbol AU, aurate. Manganese, manganate. Platinum, platinate. When these names we have to give when the complex is anionic, means when the complex is having negatively charged. When the complex is having negatively charged, we have to see the name of the metal should not be like aluminum, cobalt, gold. It ends with ATE. And you know how to identify the anionic complex, how to identify the cationic complex, and how to identify the neutral complex. Then I'm coming to this chromium. If chromium is there, the name will be chromate. Copper will be cuprate. Iron will be ferrate. Nickel will be nickelate. See, this nickelate and this is copper is quite different. Copper, it is not copperate, it is cuprate. And nickel, nickelate. Zinc, zincate. So this care we have to take when we are giving the names of the metals. Now I'm coming to the next part, that is IUPAC names of some complexes. I will now, we will start the nomenclature system. See, this is one anionic complex is given. Why this is anionic? Because already the negative charge is there. So according to the IUPAC nomenclature system of coordination compounds, we have to give the name of the ligand first. So how many, see the complex here first, Ni, CN4. So four cyanide ligands are there. So the name will be tetra first. Why it is tetra? Because four cyanides are there. Clearly see here. Four cyanides are there, and according to the IUPAC nomenclature system, if more than one same type of ligands are there, we have to use the prefix like di, tri, tetra, penta. So we are using here tetra. Tetracyano. See here, cyano. Tetracyano, because this cyanide is an anionic ligand. It ends with a, it ends with O. So it is a tetracyano, tetracyano, and see the name of the metal it is a nickel, but you are not using nickel because the complex is anionic complex. Anionic complex means the complex is negatively charged. And in this table, see, once again I am going to show this table. This table indicates clearly when the complex is anionic, what is the name of the metal? Nickelate here. See, as the nickel we are using here, so the name of the complex will be tetracyanonickelate. And after the name of this metal, we have to write its oxidation state in square bracket. So this should be in a single word. There should be no spacing between the name of the ligand, between the name of the metal, between this oxidation state. It will be single word. Completely it will be single word. There should be no any spacing between the name of the metal and name of the ligand. In the square bracket we have to write the oxidation state of this nickel. How to calculate the oxidation state of nickel? It is very easy, as there are 4 cyanides and it is having the 2 minus, so it will be 4 minus 2, it will be 2 plus 2. And iron, don't forget write the iron, because it is iron, not a complex. So if the iron is there, we have to write the name of the iron here clearly. Second example I will take here. One example it is completed. A example is completed. Now come to B. In the square bracket, see clearly it is a cobalt, it is a central metal, and there are 3. See, there are 3 oxylato ligands are there. 3 oxylato ligands are there. So the name will be first. This will be tri. See the tri. Why it is tri? Because 3 oxylato ligands are there. 3 oxylato. Why this is oxylato? Because this is again anionic ligand. This ligand is anionic. That's why it ends with ATO. Tri oxylato. Again, the name of the metal is cobaltate. See clearly, it is cobaltate. Why it is cobaltate? Because the complex is anionic. Complex is anionic because when the negatively charged complex is there, the name will be cobaltate. And in the square bracket, the Roman 3 indicates the oxidation state of the metal. And iron, don't forget write the word iron because it is iron. So I think these names are clear. Again, I am coming to the next one. We have to identify the ligand is neutral. Sorry, the ligand is negative. The complex is anionic complex. So the 6 indicates 6 cyano again, hexacyano. So 6 for the 6, we have to use this word hexa, cyano, ferrate. Why it is ferrate? Because the complex is negatively charged, so it will be Fe will be ferrate, and in the square bracket, in the normal bracket, the oxidation state is shown here with Roman 2 and iron. So I think you understand the nomenclature of these some complexes. These complexes are anionic complexes. Remember. Now I am coming to the compounds containing complex ions and simple cations. So we will take this example. If see in the left hand side, this sodium is there, this potassium is there, then again sodium is there. So if these counterions are present, already I explained when the counterions are present in the which side? Left hand side, these are the positively charged. So again the ligand will be the complex will be negatively charged. The complex will be negatively charged. There is no any charge on the complex, but only 1 minute is remaining, so I will take the one example and tomorrow we will discuss the next example. So the sodium you have to write first. This sodium you have to write first here. Sodium, then hexa. Why it is hexa? Because 6. Then nitro, this NO2, 6 nitro, cobaltate 3. Nitro indicates the bond between this cobalt and again is formed with this nitrogen, because this is